Okay, so last time we discussed the relativistic Lagrangian, and we did the covariant treatment of the relativistic Lagrangian. We also derived the equation of a free particle from that covariant treatment of that relativistic Lagrangian. So today let's get an additional term of that Lagrangian that would describe the interaction of the electron field with the electromagnetic field. Now, we know that the Lagrangian is usually written as the difference between the kinetic and the potential energies. V over here, which is the potential energy, is called the interaction part of the Lagrangian. So now we know the simple Lagrangian, we have discussed it before. The interaction term is, we will take a guess on how the interaction term could look like, right? So what is happening? Basically, we have an electron that would be interacting with the electromagnetic field. We can use the gauge potential or the electromagnetic potential A alpha, right? And so it would be interacting with this A alpha. Now the Lagrangian has units for energy, right? So to keep the units constant and everything consistent, we can write the interaction Lagrangian, which is, let me use V for that, or you can call it LINT, is minus E over gamma times C times eta alpha A alpha, right? Now this here we have the units consistent with the units for energy, and we have this electron which is interacting with this electromagnetic field. Now I can write this down. I can break this into space and time parts. So in space time parts, this will look like L interaction is equal to minus E gamma C. Now for time, we know that we have the zero components of these eta and A. So this will be eta 0, A 0. This would be just the time component, and then plus we would have this thing E over gamma C times eta I AI. Now you might notice that I used a positive signature over here, and the reason for that is because the time carries a signature, while the spatial part then would carry the opposite signature. So which is why we have this plus sign over here, because it becomes minus into minus, which is just plus, right? Okay, so now we can expand this a bit more. So this becomes minus E gamma C, and here eta 0 A 0. Now what is that? Eta 0 A 0, the product gives me gamma times C A, gamma times C A 0, but A 0 is what? Phi, right? The scalar potential, where this second term, which is E over gamma C, now eta I is gamma times Vi, right? The spatial part of the velocities. And then we have AI, where AI is the vector potential. So this means that the interaction Lagrangian becomes minus E phi plus E over C velocity times A, right? So notice that the velocity and the electromagnetic field are in the same direction. So this dot product is basically giving you the component of velocity and electromagnetic field in a same direction. So this is my interaction Lagrangian. Let's box that up. Right. Now, if we discuss the non-relativistic limit, where we do not consider space-time as this thing, so this would become L NR for non-relativistic interaction. Now, space and time are not distinguishable, so we get rid of the second term, and this becomes minus E phi. So that is the non-relativistic limit of the interaction Lagrangian. With this now, I can write down the complete Lagrangian. Let's use the symbol curly L for that. And now the non-interacting part of the Lagrangian, if you remember, we wrote it down before as minus mc squared square root of 1 minus v squared over c squared. So that is just your simple Lagrangian when we have a free particle, for example. But then you found out this interaction term, and this interaction term can be written as E over C V dot A minus E phi, right? So this is your kinetic term, and this is your interaction term. Something like that. All right, so this is now the total Lagrangian for an electromagnetic field and an electron interaction. Okay, sorry, not an electron interaction, just for the electromagnetic field. Now we can rewrite this interaction Lagrangian in its covariant form. So the covariant form of this interaction Lagrangian will look, so again we know how to rewrite in covariant form. We use tensors, and so this is minus E over gamma C times eta alpha A alpha, right? Now remember, we have already discussed what is eta alpha. Eta alpha is the derivative of position coordinate with proper time, so something like that. So if this is eta alpha, we can just put this back into this interaction Lagrangian, and this becomes minus E gamma times C, and for eta alpha we'll replace this with dx alpha by d tau, and then we have A alpha. Now we have this interaction Lagrangian. From an interaction Lagrangian, we can put this interaction Lagrangian into the equation for the action of a particle. And the action of a particle, again, for interaction, the interacting action of the particle is simply the integral of this interaction Lagrangian with respect to t. Right? So this would be minus E over gamma C dx alpha over d tau, and then we have A alpha. So we can replace this with t. This becomes minus integral E dx alpha over ds times d tau, right? Now you can rewrite this again as S interaction is equal to integral of E over C, and don't forget the minus sign, dx alpha over ds, and then this thing we can rewrite it as C times d tau. Okay, so this becomes minus integral E over C dx alpha over ds times ds. Okay, so let's go to the next page. All right, now we can write the whole action integral for a charged particle in the presence of the electromagnetic field as S is equal to, so we'll use the same thing that we derived over here, this one, and this would become integral from some S1 to S2. Remember, this S is a parameter, and this would be MC times the square root of G alpha beta dx alpha over ds times dx beta over ds, and then out the square root we have plus E by C dx alpha over ds, and of course A alpha of x, and then finally ds. This part is the non-interacting part, as we have discussed it before as well, and this one is the interacting part of the action. So this would be then the total action integral for a charged particle, for a charged particle in an EM field, electromagnetic field. Now we can derive the equation of motion for this thing by using the Euler-Lagrange equation, right? So let me write down the Lagrangian from this action. That would be just this, in the part that is inside the integral. So the Lagrangian, let's use curly L, would be minus MC square root of G alpha beta times dx alpha over ds times dx beta over ds, and then we have this term that is outside, my plus E over C dx alpha over ds, and don't forget the electromagnetic potential, which is A alpha of x. So this is my Lagrangian. Now we know that from classical mechanics, we know that we can use the Euler-Lagrange equation to derive the equation of motion for a particle that follows this particular Lagrangian. So we know that the Euler-Lagrange equation is d over ds, where ds is the position coordinate or the generalized coordinate, and this would be partial L over partial times dx alpha over ds, right? And then you subtract the derivative with respect to the space-time coordinates of the Lagrangian L and set it equal to 0. This is the Euler-Lagrange equation, and the first term of this equation we have already worked out before, and so the interaction part of the Lagrangian, which is Lint, which is minus sorry, not the interaction part, this first part, which is the non-interaction part. So I'll just call it 1, which is minus mc g alpha beta dx alpha over ds times dx beta over ds. So this means that this term partial L1 over, let's use the curly L, over partial of dx alpha over ds. This is equal to minus mc dx alpha over ds divided by the derivative of this thing, which would be the square root g alpha beta dx alpha over ds times dx beta over ds. Right. Now, just a reminder that when I write this thing as partial alpha, it just means d over dx alpha, right? So this is just a side note. Now, the second part of the Lagrangian, let's take the derivative for that, which would be L, let's call it 2, so let's use curly L, partial over partial x alpha over, partial dx alpha over ds. This is equal to, if you look at the Lagrangian, this part, this just turns out to be minus e over c a alpha of x. Now recall the Euler-Lagrange equation for the relativistic particle, for relativistic particle. We have worked that out. It is partial L over partial x alpha is equal, minus d over d tau, partial L over partial of dx alpha over ds, right? This thing, and it's equal to 0. So now let's put in some values for these terms. So for this partial L over partial x alpha, let's write that down as it is. Partial x alpha is equal to, so let's take all the rest of it to the right hand side. We worked out this term, right? And this term is basically minus e over c, as you can see, dx beta over ds, and then we have this partial over partial x alpha a. Let's give this a subscript beta now, and this would be x. All right, so we can now rewrite this thing again. We can replace this ds by c d tau, this would make it minus e over c d c squared basically now, because one c is over here and the other c comes from this replacement of ds by c d tau, right? So this will become minus e over c squared dx beta over d tau, partial over partial x alpha a beta of x. So this is the final term. So we have worked out this one. Now we'll just substitute this back into the Euler-Lagrange equation, and we'll get the equation of motion. So substituting these values that we just worked out into the Euler-Lagrange equation, we get minus d over c d tau times minus mc dx alpha over d tau, and then there's c over here as well, and divide this by the square root of g alpha beta times dx alpha over d tau times c, and then again dx beta over d tau times c. And then you have this second term, which is the interaction term minus e over c a alpha of x. Right, now you can see that these some cancellations happening over here, so you can cancel that and you're left with this thing. So we can simplify it a bit more, so let's do it. This would be minus d over c d tau, and then we have minus m times dx alpha over ds, d tau, divided by c, so this is c d tau by ds, right? So I've just worked out this term, and this would be minus e over c a alpha of x. So it looks a bit like this. Now let's work it out a bit more. This would be minus minus would become plus, so this would be plus mc m over c times d squared x alpha over d tau squared. So we're just basically multiplying the terms, plus e over c squared times dA alpha of x over d tau, minus e over c squared dx beta over d tau times partial over partial x alpha. Alpha will be a covariant index, and then you'd have a beta of x is equal to 0. Now let's clean this up a bit. This would become 1 over c factored out, and we have m d squared x alpha over d tau plus e over c dA alpha over d tau minus e over c dx beta over d tau partial alpha a beta of x. Right, so this is equal to 0 again. You can see this equation already looks like an equation of motion for a particle, right? So we can write down the second term in this equation, this one, using dA alpha over d tau equal to dx beta over d tau times partial over partial x beta a alpha. Now let's use this in this equation that we have upstairs, and so putting this back in there, this would become this equation becomes 1 over c, and that c would cancel out, so this would become basically m d squared x alpha over d tau plus e over c dx beta over d tau partial beta a alpha minus e over c dx beta over d tau partial alpha a beta of x, and this is equal to 0. So we can now make this a bit more neat, and it will become m d squared x alpha over d tau squared, which is equal to e over c partial alpha a beta minus partial beta a alpha, and this already looks something like we know, and this is multiplied by dx beta over d tau. Now remember, the electromagnetic field strength tensor, which is F mu nu, it is defined as partial mu a nu minus partial nu a mu, right? So you can just replace the indices mu and nu with alpha and beta. So this term is just the electromagnetic field strength tensor, which is now the equation would become md squared x alpha over d tau squared is equal to e over c f alpha beta times dx beta over d tau. Dx beta over d tau is just the metric tensor eta. So this would be m d squared, not the metric tensor, I meant the proper velocity, right? M d squared x alpha over d tau squared is equal to E over C F alpha beta times the proper velocity, which is, we can write it down as just, I'll write it as eta with just one index b, right? You can use any other, you can use v as well. If eta is confusing with the metric tensor, you can just say that it's v beta, right? But remember that this v is the proper velocity of the particle. Now, this equation that we have written down, I'll box this up, represents a particle that carries a charge, an electronic charge E in the external electromagnetic fields E and B, right, in the covariant form. So the force on this particle is E times E plus V over C cross B, right, where this V and B are in the same direction. We know that the derivative of the electric field with respect to time is just E times V dot E. Again, F alpha beta that we had over here, it is the field strength tensor, and it carries the components of all the electromagnetic fields. Basically, electric and magnetic fields separately are hidden inside this electromagnetic field strength tensor. So that was it for this lecture.